Hello students, welcome to the part 3 of the lecture series on filter design. We have already covered two parts of the lecture, so please go through that if you have not gone through them. And the lecture series is brought to you by Edamigo team. So let's start with the part 3. In this part we will be talking about the second method to design the digital filter. Okay, so we have already seen the backward difference method, and here we'll be talking about the another method that is called impulse invariant transformation. Okay, that is called impulse invariant transformation, a very important transformation. Okay, so let's start with, so suppose we have an analog filter with impulse response HAT. So HAT is impulse response of analog filter. ठीक है? T is the sampling interval, and Hn is the impulse response of digital filter. Okay, so impulse invariance transformation, I will be calling it IIT. Okay, so impulse invariance transformation. So Hn is equal to HAT, T equal to N capital T. Okay, so this is important. Okay, so this is actually the transformation, how to transform the analog filter into digital filter, so by simply sampling it. Okay, so this is IIT method, that is impulse invariant transformation method. Now suppose HAT has a transfer function HAS. Okay, so now let's say that HAS is equal to summation I equal to 1 to n AI upon S minus Pi. So I say that there are n number of poles in HAS, and the location of poles is P1, P2, P3 till Pn. Okay, now if I convert this into time domain HAT, we know that it will come out to be AI e to power PIT UT summation I equal to 0 to capital N. Okay, now we know that in impulse invariance transformation, Hn is equal to HAT, where T equals to N capital T. So Hn will come out to be I equals to 0 to capital N AI e to power Pi N capital T U of N capital T. Okay, now this can be written as, since variable is u, n is the variable, capital T is the sampling instant, it's a constant, so this can be written as e to power Pi capital T whole to power n u of n. That is your hn. Now, okay, so this is the transformation that will get the result, the impulse response of the digital filter. Now if I take the Z transform of this, now as we know that a to power n un has Z transform 1 upon 1 minus a Z inverse. So hz will be I equal to 0 to capital N ai upon 1 minus e to power pi capital T Z inverse. So we can say that in S plane, if I have a pole at pi, will convert into in Z plane pole at e to power pi t. So we can see that here. Okay. So pi pole will convert into a pole at e to power pi t in Z plane. Okay. So the pole transformation is pole in Z plane is equal to e to power pole in S plane multiplied by t. So this is the transformation of the pole. Okay, Z equals to e to power st. Okay, so this is actually the relationship between pole in analog domain to pole in digital domain. Okay, so this is the relationship. Now we can see that since Z is written as r e to power j sigma, or this is the digital frequency, is equals to e to power the real part of S, the analog frequency into t. So r will be equal to e to power, sorry, there has to be, sorry, e to power sigma t, or just wait a minute. So r e to power j sigma is equals to e to power sigma t e to power j omega t. So r is equal to e to power sigma t, and e to power j sigma is equal to e to power j omega t. Okay, so very important relationship it is that the magnitude of Z is equals to e to power real part of S into t, and the digital frequency is equals to continuous frequency multiplied by capital T, that is a sampling instant. So these two relationships are very important. So they can ask you these relationships in a question directly. That is, in impulse invariance method, how the digital frequency and the continuous frequencies are related, and how the magnitude of Z is related to the real part of S. These two relationships are very important. Okay. Now if I look at the mapping from Z plane into, sorry, S plane into Z plane, okay, now in the left half plane, in the left half of the S plane, sigma or the real part is less than 0. So the magnitude e to power sigma t, magnitude of z, will be less than 1. Okay, will be less than 1. So if I look at the mapping, then I can say that this whole left half plane is mapped into a circle of radius 1 in the z plane. So this is z plane, this is s plane with real part sigma and imaginary part j omega. Okay, now, okay, so the whole left half of the s plane is mapped into a unit circle. So this is what we wanted, that is, the whenever there is a stable analog filter, it will always lead to stable digital filter. Okay, always. Okay, but one very important point here it is that if we look at this equation, this one, that in z plane z is equals to r e to power j digital frequency, and this digital frequency is always from minus pi to pi only. Okay, we know that because the digital frequency axis is periodic with 2 pi, with the period of 2 pi, so it is always between minus pi and pi only. But omega, that is the continuous frequency, is from minus infinity to infinity. Okay, so if I see the mapping, then sigma that is we got is equal to omega t. So one very important point is that sigma, that is the digital frequency, will be from minus pi to pi when omega is between minus pi by capital T to pi by capital T. So this will be equal to, so sigma will be from minus pi to pi when omega is between minus 3 pi by capital T to minus pi by capital T. So sigma of the digital frequency will be from minus pi to pi when omega is from 3 pi by capital T, okay, from pi by capital T to 3 pi by capital T. So what am I saying is omega will vary from minus infinity to infinity, but the digital frequency will be always from minus pi to pi only. So we can say that whenever there is a range of omega, so I can say that whenever omega is between 2k minus 1 pi by capital T to 2k plus 1 pi by capital T, where k is integer, then this will correspond to digital frequency that is from minus pi to pi. So we can say that where k is an integer, so we can say that there is infinity to many mapping. Okay, that is omega is going from minus infinity to infinity, and this whole is mapped into sigma minus pi to pi. Okay, so there is an infinity to many mapping taking place in this kind of mapping, that is inverse impulse invariance transformation. In IIT, the continuous frequency is mapped into the discrete frequency, but this mapping is not one to one, rather it is many to one mapping. Okay, so this is very important, and this does not take place in the method 3, which is bilinear transformation. We will be talking about in the part 4 of the lecture series. So this is very important property of the impulse invariance transformation that can be asked in any of the competitive exam. That's why I have emphasized here on this property of the impulse invariance transformation. Now let's look at one example, a simple example. So question is, it is given that HAS is equals to 1 upon, sorry, it's 2 upon S plus 1 into S plus 3 and t equals to 1 seconds. Okay, so we have to find the transformation. So using IIT, so HAS is equals to 2 upon S plus 1 S plus 3. This can be written as 1 upon S plus 1 minus 1 upon S plus 3. So this is HAS. This can be written as 1 upon S minus minus 1 minus 1 upon S minus minus 3, that is HAS. Now HZ, we know the transformation 1 upon 1, or let me write the transformation for you guys. 1 upon S minus Pi is transformed into 1 upon 1 minus e to power Pi capital T Z inverse. This is the transformation formula. We know this formula. So from this equation, we can say that Hz is equals to 1 upon 1 minus e to power minus 1 Z inverse, because T is also, so in this case we can see that P1 is equal to minus 1, here P2 equals to minus 3. So capital T is 1 second, so we can say that here it is P1 into capital T, that is minus 1, and here it is, in the second part we have P2 into capital 3, that is minus 3 Z inverse. Okay, so this comes out to be 1 upon 1 minus E inverse Z inverse 1 upon 1 minus e to power minus 3 Z inverse. So we can easily put the value of e to power minus 1 and e to power minus 3. So we get that 1 upon 1 minus 0.36 Z inverse 1 minus 0.049 Z inverse. Okay, so this kind of questions can be asked in any of the competitive exam. So this much is sufficient in the case of impulse invariance transformation. So in the next part we will be looking at bilinear transformation. That will be the method 3, and that will finish the IIR filter design. So thank you guys, keep sharing the lectures and subscribe to the channel. So thank you, and give us your feedbacks.